are having midterm next Tuesday. As I said, the midterm is going to cover chapter 12 and chapter 13. So it's going to be, I believe, 4 questions or maybe 5 questions. The fifth one is like very small, that doesn't include a lot of math or any calculations. I told you that the review process, just try to get the notes, make sure that you understand the concept, solve some problems on your own, try to put yourself in the exam mode. If you want to make sure that you're really ready for the exam, try to pick a problem that you haven't solved before. When you're in the exam mode without any extra material, try to solve the problem and see if you can solve it by yourself or not. So that's how you make sure that you are ready or not. So yeah, I believe that's all. If you want to prioritize your study, notes, example in the notes, and then the homework. So if you want to do more, maybe you check the solved problems or the non-solved problems in the Deborah textbook, okay? All right, so last time we started to talk about the work and energy. We started by the definition of work, and we said work is the amount of energy that the body needed to change its position. And we start we proved that the work needed to change the position of the body from position 1 to position 2 is equal to the integration from position 1 to position 2, or let's say S1 to S2, F cosine theta ds. What does that mean? If you have your body like this, and there is a force, and this force is pushing that way, this force F, I'm not interested in the force that is in the opposite direction or it is not in the direction of the motion. Like, I'm only interested in the force that is in the direction of the motion. So this F has 2 components. One of them is in the direction of the motion, which is F cosine theta, and there's another one, F sine theta, perpendicular to the motion, and it is not equal, it doesn't contribute to your motion. Okay, let me ask you something just to make sure that you understand the concept very well. We did this last time. Let's say that this is my body, and this is a force pushing on my body that way. This force is the one that exerting work, but does the whole force make work on this body? Just one component, right? Which one? The x1, the one that F cosine theta, right? But how about the weight of the body? Does it make any work? Like, this body has a weight. Maybe it's a light weight, but it has a weight. Does it put any work on the body?
No, doesn't it produce friction?
Exactly, excellent. The thing is, the weight produces work, but indirectly. Okay, so the weight is going down, right? So it's not in the direction of the motion. So the weight, this weight, since the body's moving that way, the body's not moving up and down. Like, the weight is down. So for the weight to put work, this body needs to move up and down. If this body not moving up and down, not moving horizontally, so the weight is not putting any work. It's not exerting any work. But the thing is, the weight goes down, and you have a normal force going up, and there's a friction produced function in the normal force equal to the mu, the coefficient of friction, multiplied by the normal force that you need to overcome so that this body can move. So weight exert work, but indirectly through the friction. Okay? How about the normal force? The normal force doesn't exert work. What exert work is, so what exert work is the friction produced by the normal force, and the normal force is coming from the weight. That's how it works. Like, if you look at this body, the weight is going down, the weight is something like this, doesn't make any work, and you have the normal force going up to counter this weight, and it's not exerting any work. However, there's a friction induced here equal mu multiplied by n. That's the one that makes work. So let me ask you, is this work positive or negative? The friction force always negative work, because it's opposite of the motion. Like, your body is moving that way, the friction going the other way. So it's always negative work. If your body moving that way, the friction always in the other way, okay? All right, but talking about this, let's talk about the forces that exert work on our bodies. Okay, so let's start with number one. Work of the weight. All right, the work of the weight like if you have, let's say, this is my space that my body's moving in. This is X and this is Y. Let's say Y is vertical, okay? And this is the path that my body's moving in. My body's moving in the space. And the body was here, and somehow this body came here. And this is the location S1, and this is the location S2. So the body in general, let's say at the general location, it has a weight W. Let's find out what is the work done by the weight W on this body. Let me ask you, using your intuition, if your body was down and you somehow used your hand and move it up like this, I make it like this until it comes here. What is the forces that are exerting work here? Like here, and my hand is moving it down here. All right, my hand is giving work. I'm putting force on the body to move up. So that's what. Is it positive or negative? It's positive, right? Because it's in the direction of the motion. How about the weight? The weight is grabbing me down, and that's the one is making negative work. But let's say my hand's here, and I grab the body like here. But if it's a really heavy body, like let's say my water bottle, it's hard for me to bring it up, but it's easy for me to bring it down, right? So because I'm coming down, that's a positive work. Because why? Because the work of the weight in the same direction of the weight, which is the gravity direction, that's a positive work. But if you are trying to move the bottle up, so you are trying to overcome the gravity, which is the work have a negative work, like the weight has a negative work. But the thing is, the interesting thing about the weight, it's always going down. And we said that we are always the force needed to be in the direction of the motion. Like, okay, like this weight, the weight is not on this path. Like if the weight is, the direction of the weight is that way, and keep always parallel or always tangent to the path. So we basically say the weight multiplied by the S, like this curve, S. But the thing is, the weight is always down, so it doesn't matter if you bring this body from here to here that way, or you bring it that way to the same level, or that way, it doesn't matter the mass is, it's still the same amount of work that you have to do because the work done by the weight is equal to, let's say, U of the weight. It is gonna be equal to negative W, it's always negative, multiplied by Y2 minus Y1. I'm only interested, this is Y1, like let's say this is Y1, and this is Y2. So if your body is moving up, so your body is moving that way, so Y2 is more than Y1, and the W is gonna be negative. But if your body is moving down, so let's say your body starts from here, so Y2 is your Y1, so the other one, the bigger one is this one, okay? So, and then you are going down, so that's why the work is positive. So usually that's the rule of the work exerted by a weight. And why it's only interested in the vertical component, because I told you, like if you are pushing a body with an inclined force, it doesn't matter all the components that matter is the one in the same direction of the motion. Same thing with the weight. Weight is going down, and weight, like the body became here and it's still down. I'm only interested in the vertical direction, which is in the same direction of the weight, this height. I'm not interested in the x direction. Like I'm not interested in this. If it moved that way. If my body moved that way, there is definitely another force that caused this body to move that way, not the weight. Like it's impossible that my body, if I lift it, is gonna go X and then fall. It has to fall that way. There is definitely another force that bring it that way and made it that fall. So it's always the Y direction that is important for the weight. It doesn't matter how much X movement that my body made. All what matters is the Y direction. Okay. All right. So that's for the weight. So basically, and it's always negative. I mean, not always. I mean, like if the body's moving from up to down, it's negative. If it's from bottom to top, it's gonna be positive. Okay, that's for the weight. Let's find another interesting work formula. So the second one that we have in here is the spring work. Work of the spring force. Alright, so the general rule of the work, as we said, it's u from 1 to 2 is equal to the integration from s1 to s2 f cosine theta, or fs ds, where fs need to be in the same direction, which is equal to fs cosine theta. But I didn't put cosine theta here because of something that I'm going to tell you right now. If you have a spring, and let's say this is spring, there is a force, external force. Like let's say I have external force F. This is not the force in the spring. Like the spring is on a stretcher, and you pull the spring with a force. So you have two forces that are making work. Your external force and the forces stored internally in the spring. Okay, if you pull this side is gonna be somewhere here. It's gonna be stretched. And it's gonna be somewhere here, and this is the force F. So you stretch it this, all that distance, okay? So the thing is, the force inside the spring are always in the direction of the motion. Like if you pull the spring that way, the force inside the spring is gonna be something like this. Like this is, like if you pull the spring, there's a force inside the spring, it's F the spring, you wanna pull the spring back to its original position. What if you compress the spring? Like let's say that you put forces in the opposite direction. So the spring become like this at this point. Like you put external force that way. The spring is gonna have a counter force that way, F the spring, right? Okay, so usually the forces in the spring are in the direction of the motion. There is no theta. Here. There is no theta. Alright, unless if you have inclined the spring and your body's moving vertically. But it's still forces in the spring. Like if we are talking energy, okay, let me not to confuse you, let's focus on this and we're gonna come with an example that have inclined spring. Alright, but let me ask you a question. Is the force inside the spring? Yeah.
Sorry, if it was on an incline, wouldn't you be able to still shift the X and Y axis?
The thing is, I believe we solved a problem like this. I was thinking about it, like you have a collar here and you have a spring here, and somehow your body's moving down and the spring is something like this. The thing is, only one component of this spring is contributing to the work on this body to move up and down. Because the Fs in the spring, you have one here. Like if you get the two components, like let's say that this is theta, so F spring is this is cosine theta, and this is F sine theta. This one doesn't make work on this body. The one that contribute to the movement up and down is the vertical one. And then this one is gonna be like is gonna be countered by the normal force here. Like the spring wanna pull this puller out of the shaft, and the normal force from the shaft and the puller is countering this Fs. Anyway, we're gonna talk about it later. Let's focus on this. All right. let me ask you, is the spring force is doing positive work or negative work? Okay, let me explain it to you. Let's say that this is my spring and it's attached here, and this is the point that I'm pulling this spring from. If I'm pulling this spring, that means that the movement is that way, right? The force in the spring where? In the other direction. Let me I'm compressing the spring. So this point is gonna move inside. How about the force in the spring? It's always in the opposite direction of the motion, like the friction. The friction you push the body that way, the friction in the other way. You push it that way, the friction the other way. So the force in the spring are always negative. So this is gonna be equal to do this integration. Okay, I'm gonna integrate from S1 to S2, and this is gonna be equal to negative K multiplied by S ds. You guys remember when we have a spring, the force inside the spring is equal K multiplied by the delta inside the spring, right? So the K and how much S that you have, like this point and this point, so it's K multiplied by S. If you have a compression, so it's also K multiplied by S. And if you integrate this, can you guys integrate Ks ds? S is going to be S squared over 2, so you're going to have negative 1 over 2 Ks squared. That is the work done by a spring. That is the general formula for the work done by a spring. And at the boundary of the integration from S1 to S2. So the work done by a spring is always equal to negative 1 over 2 K of the spring, the stiffness, multiplied by S2 squared minus S1 squared, where S is measured from the unstretched position. Like let's say that you have a spring that already stretched 1 meter before the motion, and then you pulled it more and got to stretch it another 2 meters. So the initial position, which is S1, was 0.5 meter. And you pull the spring another 2 meters on top of the 0.5 meters, so the final is going to be 2.5. Okay? So S is always measured from the unstretched position. But if your spring is unstretched initially, so that means S1 is equal to 0. And then you pulled it 2 meters, so the final is going to be 2 squared. So that's the final formula for the work inside a spring. Let's put number 3 here. And actually, it's over there. Like the work done, work of a constant force moving along a straight line. Number 3, work of a constant force moving along straight line. All right, so can you see this? This is the work done by a force that is variable. So that's why the force is inside the integration. But if you have your integration has a constant force, you can take the constant force out of the integration. But let's say the force keeps changing over the path of the motion. Like the force that you are putting is not constant, it's changing. And I told you that the force is changing over time, and it's equal to 5t squared plus 1. So you have to put it here, 5t squared over 1. Or changing function in ds, so you have like put it 5s squared plus 2. But what if I said that you have a constant force of 400 Newton? So if it's constant, basically I can say the work done by this force is equal to, I can take F out, and I also can take cosine theta out, and then I can integrate ds from S1 to S2, so this is going to be F cosine theta multiplied by S. That is the final force. And this, the boundary of integration is from S1 to S2, and this is going to be F cosine theta S2 minus S1. For the total S between this distance. Like let's say this body here is S1, and then this body moved here and get to S2, so the difference between them is S2 minus S1. That is basically most of the types of forces that we are going to deal with. Either a constant force on a straight line, or you're having a spring force, and definitely the wave force. So all these are forces that we are going to deal with in our problems. Right, I have an example here. right, for this example, it says that we have this 350-pound automobile shown in the figure, travels down the road that has 10-degree inclined angle at the speed 20 feet per second. If the driver jams on the brakes, causing his wheels to lock, determine how far S the tires skid on the road, given that the coefficient of kinetic friction between the wheels and the road UK is equal to 0.5. All right, let's translate this problem. You have a road, like any roads outside, and have a little bit of inclination, like this angle is 10 degrees. You barely can feel it. 10 degrees. And your car is like somewhere here. Somewhere like this. This is your car, and your car is moving at this instant with the speed V, that's the initial speed, 20 feet per second. All right, I'm trying to translate here. And the weight of the car, since I give it in pounds, 350 pounds. That's not mass, that's weight, 350 pounds. Okay, it moves with 20 feet per second. If the driver jams on the brake, like at this instant, you put all your feet on the brake, and this car starts like all the, what is he saying jams by the brakes? That means the motor force is not part of the problem, like the motor is not working. Once you jam on the brakes, it's done, and all the wheels are locked, are not moving, so that's, he said the wheels are locked, and it's moving gravitationally down. So that's why you don't need what is the motor force of the car, okay? So once you jam on the brake, the car is not gonna stop right away. It's gonna take a little bit of inertia until it goes down and stop. Okay, and he's asking for, determine how far S, like the distance from here, until this car comes here. The tires is skid on the road. So the tires is gonna skid until some point, and then the end is gonna come here. You guys tell me, what is the velocity? Just make sure, but I think this example need me to introduce another concept before I get into it, because we didn't take the conservation of energy. Example. Okay, before we solve this example, we're gonna get back because I have to introduce concept of the work and energy before it. I want to solve an example on this concept that only include work and doesn't include energy. Okay, basically, if I give you velocity in an example, that's why how I like when I like start thinking, oh, there's a velocity, but we didn't deal with any velocity here. It's all distance, like force multiplied by distance, spring multiplied by distance, and that's also keeps you thinking, when I give you an example in a problem, what approach that I should use it in. Like if you have no velocities, the work is gonna work for you. They are all multiplied by s, there's no velocity here. But if I give you velocity, my head is like, oh, that's work and energy. So I mean, like we are gonna take it in a little bit. But let's actually put another example. Actually, I'm gonna put it here. Example 14.1. For example 14.1, just going to read the problem for you. For you, so it says that you have an inclined surface, and this surface inclined by angle 30 degrees, and you have a body here, like a crate or something, and this crate has a mass M. This mass is equal to 10 kilograms. And this body is attached to a spring. Say the spring is something like this. And there's an external force B. But before I put the external force, let's put the stiffness of the spring first. The spring is equal to 30 Newton per meter. There is an external force B. This force is horizontal and it's in that direction. B is equal to 400 Newton. I give you an information about this spring. The spring in that position was stretched by 0.5 meter. And the force B kept pushing this body all the way up until this body became somewhere here at S distance from the original position of 2 meters. Okay? Alright. So I have my body here attached to a spring on an inclined surface 30-degree angle. Have a force 400 Newton are pushing all the way horizontally, but the body is keep going up. And what this force was able to overcome what? To overcome a bunch of forces. And actually I gave you it's moving on a smooth surface. Like what does it mean by a smooth surface? The friction doesn't put anywhere. It's a smooth, okay? So guys, tell me, given these all forces, what forces are exerting work here? Number one, weight, okay? Weight is going down. I mean, like, the weight is going down. I don't care about the horizontal movement. I care about the vertical movement. I don't care, like, the weight is not gonna be multiplied by 2 meters. It's gonna be multiplied by what? The vertical component of the 2 meters, okay? Because the weight is going down. How about the B? The B is putting work or no? Given that it's moving up. The horizontal component of B is the one that makes work, because B, or the component in the direction of the movement, okay? Like it's the same thing. Like if you multiply B by cosine this C theta and multiply it by 2 meters, it's gonna give you the same thing if you take the horizontal component of the 2 meters and multiply it by the 400. Both are the same solution. What else? So it's B and weight. There's another one.
Spring force.
The spring force. This body wanna move up, the spring force wanna pull it down. But let me ask you, is the spring force positive or negative?
Negative.
Negative. Is the weight positive or negative? Negative. Is the B positive or negative? Positive, because the body is going up and the B, the vertical component of the B is also going up. Okay? So let's find them one by one. The first one that I wanna find, the number one, the force done by the horizontal force. Work done by the horizontal force. Since the horizontal force is constant, I can basically apply this rule. I can say that the U done by B is equal to F cosine theta multiplied by S2 minus S1. Okay, so first I have to find the F cosine theta. I need to find this theta is 30 degrees. So it's gonna be equal to 400 cosine 30 degrees. So right now this is my body. I have here B is something like this, that's B. And I only need the B in the direction of the movement, that's B, which is B cosine 30 here, multiplied by S2 minus S1, which is gonna be 2 meters. Or you can actually say S here was 0.5 and S here was 2.5. So you can say 2.5 minus 0.5, because I said that the spring was unstretched for 0.5 meter, and then you stretch it all the way up 2 meters, so the difference is 2 meters. So you either put it 2 meters or 2.5 minus 0.5, either is fine. And then if you calculate this, it's gonna give you positive 692.82 Newton meter. And Newton meter also we can write it as joule. Joule is a unit that measures work, which is equivalent to Newton multiplied by meter. Okay, so that's number one. Number two, the spring force. The spring, or let's say the work done by spring force. Work done by spring force. Okay, for the work done by the spring force, I have the rule over there. The U spring is always negative 1 over 2 K multiplied by S2 squared minus S1 squared. Alright, so I can put negative 1 over 2. I give you that the K of the spring is 30. And I told you it was stretched 0.5 and then you pushed it another 2 meters. And all the pushing in the same direction of the spring. Like the spring in the same direction of the movement. So the final stretching was at 2.5 square and the initial stretching was at 0.5 square. So when you solve this, this is gonna give you negative 90 Newton meter. The force number 3 is the weight. Work. Can you guys see this? Going down. Should I write it up? Number 3, work done by weight. Okay, I have the rule here. The U by weight is negative W Y2 minus Y1. Let's see if it's positive or negative. Negative W, so W is 10 kilograms, so it's gonna be 10 multiplied by the gravitational acceleration, which is going to be 9.81 because that's metric units. It's American unit, so it's going to be 62.2. All right, what is Y2? Y2 is this Y. That's Y2. Y1 is equal to 0. If you want to make your datum at 0.5, so that is going to be equal to Y2. You can do it both are going to be the same. The Y2 is going to be 2.5, but Y1 is going to be negative, it's going to be positive 5. Okay? So the thing is, you can pick your datum. Either the body started here, and then, I mean, like your datum is here, and your body as 0.5, and then become 2.5. Or you can make it here, the body is 0, and then goes 2. It's going to be the same difference. All right? Okay, so I need to find Y2. If you know that this is 2, and this is 30, can you guys find Y? Okay, so what is sine 30? It's gonna be equal to Y over 2, right? So Y is equal to sine 30, right? Or the sine component of the 2. So this means that Y2 is going to be equal to 2 sine 30 and Y1 is equal to 0. So this is going to give you negative 98.1 Newton meter. Alright, the way that I did it here is different, but it's going to give you the same answer. What I did here, I tried to find the weight component in the direction of the 2 meter. Like, okay, like I said that the weight is coming down like this. The weight has a component in this direction and component in this direction, okay? So this angle is 30 degrees, but this angle is 60 degrees. So I got the weight multiplied by cosine 60, and that's the weight in the opposite direction of the motion, like the motion is that way and the weight is going down, and this is gonna multiply by the 2. So if you try to find cosine 60 is the same like sine 30, they have the same value. So both are right.
If you use instead of 2.5 and 0.5, 2 and 0 and 0 will be the same.
What do you mean 0 and 2.5?
Like there in those the previous equations. instead of 2.5 and 0.
This one?
Yeah. if
That's
you
for the
use-
spring.
Oh, okay.
That's the spring, not the weight.
Oh, okay, okay.
So you're asking about the spring or the weight?
No, I'm asking that if instead of using 2.5 and 0.5, you use only the distance of the graph. Like 2
No,
and
you
0.
can't, because the spring started on a stretching.
Oh, okay.
You can't, in the spring you can't, you have to include everything.
Okay.
Because it's already started with work. So the work at the start wasn't 0.
Right. Oh.
So you have to put the final and the initial.
Okay.
But in terms of weight, it doesn't matter, because like it's just the difference. Like it's not square, it's linear.
Right.
Okay. All right. So either is fine. You either like y2 minus y1. I know that y2 is this part. So or you can pick the difference. The difference between these two is 2. You try to find the vertical component of the 2, which is y, which is 2 sine 30. And then once you multiply this together, it's going to be equal to negative 98.1 Newton meter. So it's basically, you either try to find the vertical component that matches the weight direction. So here I found that the vertical component is 2 sine 30. Or you try to find the component that matches the movement. So I find the weight component that in the same direction of the movement, which is the one that I did here. So either is fine. So what I'm trying to do right now, I'm trying to put the work to be in the same direction of the force. Like if your body, like my body, the weight is like, oh, where's the body? Yeah, the bottle, like let's say that this is my body, like here, okay? The weight is going down. If it comes here, it needs to be multiplied by this vertical distance. Or I have to find the weight component in this direction that it moved the 2 meters. So the weight component in this direction is the cosine component. So I multiply the cosine component by 2 meters. So either is fine. All right, so I found all the work that is being done on this body, the work by the spring, the work by the weight, and the work done by the horizontal force. So if you want to find the U total, it's going to be equal to the U done by B, and the U done by the spring, and the U done by the weight. And this is going to be equal to 692.82 minus 90 minus 98.1, and this is going to give us 504.72 Newton meter or joule. Does anybody have any question? I just did direct application in the equations that I just gave to you. I put 3 equations. One is the work done by the weight, one is the work done by the spring, and one is the work done by a constant force. And I did just direct application in them. I did some geometry just to find out what is the distance that I'm multiplying.
For the work done by the weight, what would change where to make like y1 not equal to 0? Like what, or is it always going to be 0 because it's like your starting point?
Well, okay, let's say here, and let's say this is my weight, okay? And this is the final position, okay? So the thing is, what I did here, I picked that my datum is that one. That's where I'm measuring y1 and y2. The thing is, since my body started from here, so y1 is equal to 0, right? And this is the final is y2. But actually, you can pick your datum anywhere. I can pick my datum here. And I can say, okay, y1 is equal to 10, and y2 is equal to 12. So basically, you take 12 minus 10 is going to give you 2. You can pick the datum anywhere. It's going to give you the same thing. If you pick it here, and here it says that this one is, let's put the distance. This point is 0. This point is where the S is started, so this is 0.5, and this is 2. Okay? So the thing is, you need to find out what is this y, the total weight. This is equal, like if this is 30 degrees, so this is equal to 2.5 sine 30. Okay? And this one is 0.5 sine 30. So when you come here and say negative w, y2 minus y1, so it's going to be negative w, y2 is 2.5 sine 30 minus 0.5 sine 30. So it's gonna be also 2 sine 30. Even if you take it all the way down, choose your datum anywhere, it's gonna be the same thing. Alright, let's get to the concept of work and energy so that we can solve the example that we have it here. Solve with another example here. Alright, so let's dive in deep in the energy. We have done all this, we only dealing with work. We didn't deal with energy. But let's say how we can convert work and energy or how we can combine them together. The thing is, I wanna just revise with you, if we have a curved bass and our body is here and came here, and let's say that there's a force on this body and this force is F. The F has a component tangent, a normal component, or has an R and theta component. So, but let's focus on the tangent and normal component. Like let's say that your like F tangent, like this is the sum of the forces in the tangent direction and the sum of the forces in the normal direction. Let me ask you, if your body is moving on a bass, okay? Which component of these forces making work? The tangent component or the normal component? It is always the tangent component because this is in the same direction of the movement. The normal component is perpendicular to the movement. It's not making any work in that direction. Like if I'm moving, so all the work that I'm doing is in the direction of the bass. So if I'm driving with my car on a curve, the motor is in the direction of the bass, and this is the only one that is making work. Yeah.
Isn't there a force going in the normal direction?
Yeah, but this is something that you are overcoming with the normal acceleration. Like it's like working a different direction. Like it's in the other, but in this direction, where's the velocity? That's where you are moving. Like if this body, where's the here? This one is moving that way, and your car is driving that way. So it's always in the direction of the velocity. That's where you are having work. If you are moving on a curve, the perpendicular component is not contributed to the work in the direction that we are working with. So it's usually the F tangent that we are dealing with. And we know that the F tangent, sum of the forces in the tangent direction is equal to MA tangent. And the force or the or how this the tangent acceleration is developed is like when you like put your feet on the gas that we are you giving your car an acceleration to move with. But the anormal, this one, it gets generated from the velocity, but in the other direction. The one that we are not trying or are not interested in to find what is the work in this direction. We are trying to find a work in the tangent direction. Okay, so that's actually where we at right now. Like the force is equal to the mass multiplied by the acceleration. And the thing is, we know that the A tangent is equal to dE tangent dt. And also, this is equal to V dV over ds, if you guys remember, right? We have done this before. We said that dVt is equal to ds dt, and we said that dt is equal to ds over dv, and also equal to, sorry, this is dt here, and this is also equal to dvt over a tangent, and we were able before to find the a tangent as a function of v and ds. Like if you guys remember, we had from before, ads equal to vdv. We wrote this equation many times. All right, so basically I can take this and substitute here and say that the sum of the forces in the tangent direction equal to the mass multiplied by v dv over ds. And then I can rearrange this equation. It's going to be the sum of f to t, and then I'm going to have ds here, and this is going to be equal mv dv. Since I have differentials in this equation, I can integrate the both hand side. This side, when I integrate it, since I have ds here, this is going to be from s1 to s2, and this is going to be from v1 to v2, the final v. All right, so let's get this integration done. Okay, so this integration, if I integrate this, actually I can take the summation outside of the integration and integrate all the forces from S1 to S2 of F tangent ds, and this is going to be equal to, if I integrate mv dv, is going to be equal to half mv squared, and the boundaries of the integration from v1 to v2, if I integrated v, is going to be v squared over 2, and it's going to be something like this. So basically this is going to be equal to half mv2 squared minus half mv1 squared. Do you guys know what is this component, half mv squared? That's kinetic energy. So the kinetic energy is always equal to half the mass multiplied by v squared. So what I did right now, S1 to S2, when you multiply force by distance, that is the general equation of work, this equation. That is work. And that is energy. So, and this is, we can say this is the work done from point 1 to get to point 2, and this is your kinetic energy at point 2 minus your kinetic energy at point 1. What does that mean? Like, it means that if your body's here and your body came here somehow, by exerting work from 1 to 2, you did some work, 1 to 2. This 1 to 2, your energy was T1 here, becomes T2 here. Like, we can say that your energy at the final position is equal to your energy at the initial position plus the work that you have done it from 1 to 2. Like, send this to the other side. So that means you have an energy here and you put some work, so you convert it in energy. Like, think about it like that way. If you have a mountain and you have something that you are carrying on and you are taking all the way up, here you have a kinetic energy. Like, let's say it's 0. You put some work and this body move all the way up and it has different kinetic energy. That's what we are trying to do. So that's why here where the velocity is going to show up, like the example of the car over there. The car started with a specific velocity. So you are having mv1 with a value. And you put some work to get to another value. Okay? Alright, does anybody have any questions so far? This is called the principle of work and energy. How we can transform work into energy. Basically, the work is equal to your energy at the final position minus your energy at the initial position. And actually that's the definition of the work, is the amount of energy that you put in a specific body to change its position. Okay? Like, let's give the same example here. Like, let's say I'm pushing this and this one is moving with a very low velocity, and then I give much more forces and it's then moving fast. So this is have a kinetic energy with the velocity here, have half mv1 square, which is very slow, and then I put a lot of force, and then the movement is keep getting higher until I get to this position with much higher velocity. Why the velocity is higher? Because I put more work, I put more force. So the force that I put more on my body got converted to more energy. Okay, you guys understand this? So let's solve an example, this example, and see how we can use this principle. Let's see if I don't. Yeah, just have some notes for you. This note is, it says, unlike work, which can be either positive or negative, the kinetic energy is always positive, regardless of the direction of the motion of the particle. The energy is always positive, there is no negative energy, okay? Like, why? Because V is always a square. It doesn't matter the direction of the V, either in the positive direction or in the negative direction. It's gonna always be squared, so that's the energy. Same thing with the spring, like we are gonna find the work done. We're gonna talk about the potential energy and the spring energy and all of these, which is called elastic energy, maybe next time. But any energy is always positive. It's not like the work is positive or negative. So never, when I ask you find or calculate the energy at a specific location, if you find it negative, that means there is something wrong that you have done in your calculation. It's always positive. Okay, and yeah, here's some side notes, but it's not that much important. Let's solve this problem. Okay, let's get to the problem that we put first. That's why I needed to introduce the concept of work and energy. Since we have velocity here, we need to use it over there. Okay, so in this problem, let's get back. We said that we have a car that is 3,500 pounds and travels down at 10-degree inclined road, this road. If the driver jams on the brakes, causing his wheels to lock, determine how far the tires escape. Okay, let me ask you, what is the initial velocity of this car? 20 feet per second, this is the initial velocity. Then you jammed on the brakes. What is your final velocity? What? Final velocity? 0, right? You jammed on the brakes until the car move until it is stopped. So the V2 is equal to 0. Right? So actually right now I have the initial and the final kinetic energy. I have all this, right? We need to find this, the work. So what I give you here that the mu is equal to 0.5. Yeah, and I give you the weight, and that's all what you need to solve the problem. Alright, let's find out what is the forces that makes work on this car.
Horizontal component of weight. Horizontal component of weight.
Of the weight, that's right. So let's put this car here as a mass, like here. This car has a weight going down, right? So in the direction of the movement, like if you try to find the component of this weight, you are gonna find one that way and one that way. So let's say that this is 10 degrees. So this angle is 10 degrees. So you have here W to sine 10. And here you have W sine 10. What else?
Friction.
The friction, I give you mu k. So you have the friction component. Since the car is moving that way, so you have the friction component that way. F friction. Okay, so that's the two forces that makes work. So let's find the total work by these two forces, but to do this, I need to find what is the value of F of friction. To find the value of F of friction, I have to do some Newtonian kinetics to do this. I have, let's actually do this in a much better way. Just eraser. Bigger so you guys can imagine this is the body. Alright. I have the weight is going down. I have the normal force is gonna respond to this. I have the F friction. So these are the forces that I have. So if I wanna do, like, let's say that's the free body diagram. Let's do the kinetic diagram. So I have, this is my body. My body is moving down. I'm gonna say that this is X, and I'm gonna say that this is Y. So this is the normal force. Sorry, the weight is not in that direction. Is always vertical, something like this, that's the number. Alright, so the weight is going to have two components, one in the negative y direction, like this is the component of the weight in that direction, and another component of the weight is going to be in that direction. And we did it in a little bit, like we had this something like here, we said that the weight is going down. I want to find the component that is going here, and the component that is going this way. We said that this angle is 10, so we have W cosine 10 and W sine 10. So this is W sine 10, and this is W cosine 10. The normal force is going in the y direction, the F of friction is in the negative x direction. So the only component that I need to analyze it in x and y is the weight. So I can say in x direction, I can say that the sum of the forces in x is equal to max. And in y direction, that the sum of the forces in the y direction equal to may direction. You guys tell me, what is the direction in the, what is the acceleration in the y direction? 0. So this is equal to 0. What is the forces in the y direction? This direction. Y. I have the normal force and it's positive, and I have the weight, which is negative W cosine 10. So the normal force, and all this is equal to 0. So the normal force is going to be equal to W cosine 10, and this is means 350 pounds cosine 10, and this is going to be equal to 3, 4, 6.8. So I have to do some Newtonian kinetics from chapter 3 so that I can find the value of the forces. Alright, if you know the normal force is this value, can you find the force of the friction? Yes, because we know that the F of friction is always equal to the mu of the friction multiplied by the normal force. So I have the mu given 0.5, and normal force we just calculated it. It's 344, 6.8, so this is going to give us 1723.4 Newton. I got the friction force. Why I'm doing all this, I already know the weight, it's given, but I don't know what is the value of the friction. And to find the value of the friction, I need to find the value of the normal force. And to find the value of the normal force, I have to use Newtonian kinetics in the direction of the normal force, which is the y direction. And once I solve it, I'm gonna find the value of the normal force to get F friction. Okay, so right now I have F of friction, and my body is something like this, and F of friction is that way, and the weight component, you know that the weight is coming that way, and the weight component is going that way, this weight component, the W sine 10. So, the thing is, this body is gonna stop somewhere here, and has to cut a distance S, that we don't know yet, all right? Until it comes to velocity v0, and the velocity here was v equal 20. So basically, since you have the component of the weight, you can multiply it by S so that you can get the work. And the friction is basically multiplied by S is gonna give you how much work is done by the friction. So I can say that, I can use the rule over there. The work from 1 to 2 is equal to T2 minus T1. The work from 1 to 2 is the work done by the weight, so you are going to have positive W sine 10 multiplied by S. That's the work done by the various force. The work done by the friction is negative F of friction multiplied by S is going to be equal to half mv2 squared minus half mv1 squared. Okay? So let's substitute. I have the weight of the car is 350 pounds, sine 10, multiplied by the S, I don't know it. Friction is 1723.4 multiplied by S. MV2, I know that V2 is equal to 0. V1 is equal to 20, so I know that this is 0 minus 1 over 2. The mass is 350 over 32.2 because the weight is in pounds, so I need to convert it to mass. And this multiplied by 20 squared. So this is one equation function in S. Like you can take S as a common factor and divide this over. It's gonna give you that S is equal to 19.5 feet, not meter. All right, let's see what I have done here. Take it step by step. I give you a car, it starts at velocity 20, you push the brakes, stop after a distance S. I ask you to try to find the distances. So since I give you velocities, how? I give you the initial velocity, and indirectly I told you what is the final velocity. I didn't tell you it's a 0, but indirectly when you push the brakes, you definitely are gonna stop. So you know the initial and final velocity. So you know the right hand side. This is half mv squared, and this is half mv squared, which is 0. So my problem is to find the forces that are doing work from this location to this location. The forces that are doing work here is the weight of the car is trying to pull the car down, and the friction is trying to resist the weight from going down. So I use the Newtonian in the direction of the weight to find the F of friction. And that's the stuff that we have done over the last week. Once I find F of friction, and I find the weight component, these two forces are in the same direction of the S. Okay? So when I find these two forces, I multiply by the distance. Like F of friction, if you want to find the force, the work done by F of friction, you multiply, like here, I told you that F of friction is 100, and you cut distance 10, you multiply 100 by 10. That's the force, the work done by the friction, because the friction is always in the direction of the movement. It doesn't have to be theta here. Like let's say the friction like on this curved path. This is S is equal, like when you find the distance here, this is S is equal 25 meter. And the F of friction is equal to 100 Newton. So basically if you want to find the work done by the friction, it is always negative, and it's it's the F of friction multiplied by S right away. There's no theta between them. Okay, yeah, I put it here negative, and then you will find S. By the way, there's another way to solve this problem, but it's gonna take 2 steps. Yeah. You have a question?
Yeah.
Sure.
To find the friction force, is it possible to solve for n with the
Solve
y
for
bits?
n?
Yes, so for the normal force, using the work, the y component of work, and then use n to find the x component of the normal force.
But that's what we did here.
Oh, that's
Like, here's the weight, and we got N here. Like, we got N minus W cosine 10 equal to 0. And then we got N, and once we got N, we multiplied by mu K, and then we got the F of friction. Or U, yeah.
I understand that U from 1 to 2 has to be the sum of forces acting on the object, right?
U from 1 to 2 is the sum of the work.
The work.
Yeah,
But
the forces that are doing work.
The work of the weight isn't it negative? Like
No, the weight is going down. Like, okay,
no, the thing is that because of the formula it's negative at the beginning.
okay, but I told you, you can use the formula, but also you can use your intuition. This body's moving down, so the work is positive.
Oh, because it's on the
It's going down, but if the car is going up, the work is gonna be negative. You can do the same thing. Like, you can say, this is.
because
what
it's
I-
going in the direction of the
Yeah, like, okay, you can use also the formula. Like, this is your body here, and it's gonna come down here, okay? So, this is your y1, and this is your y2. It's going down negative, right? So this is negative, I don't know. How much is it? Like, let's say it's S, like, let's say that this is S, and this is 10 degree. So the vertical distance here you are gonna go down is S, S sine theta. Okay? So you went down, y1 is bigger than y2. So when you say that negative W, so this is gonna be negative S sine theta minus y1, which is gonna be 0. So when you multiply the negative by negative, it's gonna give you positive.
Okay, now makes
Okay?
sense. Now
So when you go down, you are making negative distance. When you go up, you are making positive distance. So it's gonna be, but you can actually cancel the sign from your head, and also if the body's going down in the direction of the gravity, that's positive work. If it's going up, that's a negative work. So that's what I did. Yeah, let me get back to your question about the friction. The first one who asked that question, did I answer you?
Yes.
Okay. All right, so what I want to say here, I can solve the same problem if I solved it this equation. You remember I put all the forces in the x direction, and then the forces in the y direction. You didn't ask me, you solved the forces in the y direction, but you didn't solve the force in the x direction. I did this because I know that ay is equal to 0, and that's an easy equation, give me the value of the normal force, and I use it to get the friction. But this equation, there's an acceleration in the x direction. So, if you solved this using Newtonian kinetics, you also can get this. Because if you put all the forces in the x, you will find that you only have W and the friction in the x direction. You can put them, both of them, here, and this is equal to m multiplied by ax. It's gonna be function in ax, and if you find ax, and you also have the velocities at the 0, like v node and v final, you can use these to get s from this equation. Like, you remember ads is equal to vdv. Like, you know a, sorry, you already got a from this equation. You already know the velocities, the final and the end one, and you want to get s. So if you guys remember, we had a rule here that was like saying half v2 square, v square minus v node square is going to be equal to the integration of ads from s1 to s2. If you solve it this, you are going to get s from this equation. And that actually makes sense, because the way that we proved this rule, the kinetic energy rule, we substituted with, I believe, yeah, here. We use this, the relationship between the acceleration and the velocity and the distance, ds. So it is the same thing. So basically, you can solve this problem using Newtonian kinetics by itself, but you are going to take 2 steps. The first step is that you have to solve this equation. That's step number 1. Step number 2, once you solve this equation and get A, you have to go to chapter 12 to get S. So you use 2 chapters to do this. But what I did with the work and energy, I only solved one equation, this equation. U equal to T2 minus T1. T1 is equal half mv half m20 squared, and this one is equal to 0, and I only want to find these forces, so it's only one step. Maybe I solved it in the in the notes in 2 ways. Maybe you check the other way and see which one is easier for you. But if in the exam I told you to use the concept of work and energy to solve a problem, if you use another concept, you might not get any credit. So you have to follow what I'm asking you for. But if I ask you to solve the problem, and I didn't specifically say use a specific equation, so you can solve it whatever you want. Okay? All right, so next time we only are gonna have the exam. We're gonna use the 75 minutes of the lecture, and then we are gonna continue on the work and energy on Thursday, 1 week from now. By the way, I uploaded a survey for the class, like a Google survey. Try to fill the survey. I just want to need your input if there's anything need to be changed, if you have any concerns, so that we can address this for the rest of the semester. Yeah.